everybody. Welcome to the lesson on confidence intervals. So at this point in the course, we're finished with probability, no more probability, and we're going to be looking at inferential statistics. And if you remember from the beginning of the course when we talked about these for the first time, these are a set of methods that allow us to make generalizations from a sample to the population. In other words, they allow us to infer to the population. So there's two main tools. There's confidence intervals and there's hypothesis tests. This week we're going to be looking at confidence intervals, and then we're going to be looking at hypothesis tests for pretty much the whole rest of the course. So this is our 1 week on confidence intervals. So just a few things to remember before we continue. A statistic is a quantity that's based on a sample, such as a sample mean, and a parameter is a quantity that's based on a population, such as a population mean. X bar is the symbol for the sample mean, and mu is the symbol for the population mean. And then likewise, S is the sample standard deviation, and sigma is the population standard deviation. So for our confidence interval, we're interested in two quantities. The first one is the point estimate. The point estimate is if we had to pick one number that would be our best guess for the value of a parameter, that would be the point estimate. Every parameter has a corresponding statistic that is its point estimate. So for the population mean, its best estimate is the sample mean. And for the population standard deviation, its best estimate is the sample standard deviation. So the process here is we want to know the population mean, but we don't have the entire population. So we can't calculate a mean if we don't have the whole population. So instead we take a sample, and we hope that we've got a good quality sample, meaning it's representative. And if that's the case, then X bar is expected to give us a good estimate for mu. And if you remember, the central limit theorem told us that the sample mean is centered around the population mean. So that's the first quantity that we're interested in. Working toward the next one then, we know that X bar should be a pretty good estimate for mu, but just due to the nature of sampling, X bar is not likely to be exactly mu. So if we take a sample, we collect the mean, the odds of it being exactly the same as the mean we're trying to estimate are just slim, just because we're only getting a portion of the population in our sample. So this is called sampling error, which doesn't mean that somebody made a mistake. It's just, like I have written here, it's the natural tendency for the statistic not to be exactly equal to the parameter. So we're going to calculate a confidence interval so that we have a pretty good idea of a range of values that are likely to include the parameter. Okay? And we construct this confidence interval, and this is why it's called a confidence interval, so that we are usually 95%, but sometimes 90% or sometimes 99% confident that the parameter is included in this interval that we construct. So the second quantity we're interested in, we've got our point estimate, which is X bar, is the margin of error. You've probably heard of this before. Around election time, they'll say candidate so-and-so is beating candidate so-and-so by 1 percentage point with a margin of error of 2 percentage points. Margin of error just means we think it could go that far in either direction from our estimate. So we might write a confidence interval this way in margin of error form. x bar plus or minus the margin of error, or we could write it as an interval where it's the lower limit is x bar minus the margin of error, and the upper limit is x bar plus the margin of error. And just to kind of go easy on you, we're not going to do any hand calculations here. We're going to do all of them in SPSS. So I'm not going to go through this to get this SPSS output because we've done exactly this calculation repeatedly. If you get the output from the explore function under Analyze Descriptive Statistics, Explore, and then put your variable in the dependent list, you'll get this output. And these two rows here give you the confidence interval. So, and if you want to follow along, if you want to pull up the attention span data set and then run your explore function based on the number of hours per week spent watching TV, you'll get this confidence interval, which is 7.7727 hours up to 10.7273 hours per week. We'll talk about interpretation a little more in just a minute. So from looking at this output, you can see the interval and you can see the sample mean. If they ever don't give you the sample mean, all you have to do is average the lower and upper limits together. So if you did 7.7727, add 10.7273, and then divide the result by 2, you'd get 9.25. All right, so you don't have to be told the sample mean if they give you the confidence interval. You can also tell what the margin of error is if they give you the confidence interval. And to do that, all you have to do is take the upper limit and subtract the sample mean. Or you could take the sample mean and subtract the lower limit. It's the same thing. All right, so if they give you the confidence interval, to find the sample mean, you just have to take the average of the two. And then to find the margin of error, take our upper limit, subtract the sample mean, and that gives us the margin of error. So our estimate then is 9.25 hours per week, plus or minus 1.4773 hours per week. So now let's move on to talk about interpretations. Every time you give me a confidence interval, I want to see a statement of interpretation. You should never write a confidence interval, to turn into me anyway, without giving a sentence of interpretation. All right, so there are several interpretations that will work, that are valid, and then there are some that won't work, and we're going to talk about several of these. So here are some valid interpretations. It would be correct to say with 95% confidence the mean amount of television watched per week for all middle school students is what this data set was for. This data set was for a sample of middle school students, so we are inferring to the population. So it would be correct to say with 95% confidence the mean amount of television watched per week is between 7.77 and 10.73 hours per week. It would be correct to say we are 95% confident the true mean, which is the population mean amount of television watched per week, is between those two values. Now I want to look at some incorrect interpretations and what the problem is with them. First of all, one interpretation that people have been known to write is the mean amount of television watched by adolescents is between these two numbers. The problem is we can't say that with such certainty. You always have to leave yourself an out. we need to include that business at the beginning of the statement saying with 95% confidence. Okay? Because we don't know that for sure. Next one. We are 95% confident the mean amount of television watched by all adolescents falls between those two values. I realize this may sound picky, but saying the word falls makes it sound like the population mean is moving around. I picture a marble on a roulette wheel jumping around until it lands someplace. But that's not what's going on with the population mean. The population mean is a fixed quantity. It doesn't move around. So if you say falls, it makes it sound like it's moving around when it's really not. So we're going to avoid the use of the word falls. We are 95% confident that the mean amount of television watched by the sample of adolescents is in the interval. The problem here is that you're saying we're 95% confident that the sample mean is in that interval. We know what the sample mean is. There is no question what the sample mean is. We know it for 100% certainty. It's the population mean that we're trying to make inference about. So that's what we are trying to infer to. So we'd want that to be watched by the population of adolescents instead of the sample. And this last one, 95% of all adolescents watch between 7.77 hours and 10.73 hours of television per week. The problem there is that it's not about the proportion of adolescents who watch that much TV. It's about how confident we are that the population mean is in that interval. All right? So, in order to be able to do this confidence interval that we're trying to do, we need one or both of these things to be true. And I think you'll recognize these from when we did the central limit theorem. And in fact, this formula comes directly from the central limit theorem. So we need the data to follow a normal distribution. You could look at that. You could determine this by looking at a histogram and seeing that it's approximately bell-shaped. Or the problem might just say, go ahead and assume a normal distribution. But the good thing is that according to the central limit theorem, we can still assume that x bar follows a normal distribution as long as we have a large sample size. So we only need one of these two things to be true. So if you look at your SPSS output and see that the sample size is large, then you don't need to check normality. All right, and if you're told that the data follows a normal distribution, or if you see that it does, you don't have to worry about the sample size. You only need one of those two things to be true. All right, so let's first look at the SPSS output for our example. We see that the sample size is 40. That means that we're good to go on the confidence interval. If that hadn't been the case, if it had been a smaller sample size, we would need to look at the histogram. Okay. If we don't have either one of those things true, then we just shouldn't report the confidence interval. So we need one of those two things to be true in order for that to be a valid way of estimating the population mean. Next thing I should say is that it is possible, if you're looking at a confidence interval, to determine whether a hypothesized value of the parameter is a reasonable guess. So based on our confidence interval that we got, which was 7.77 hours up to 10.73 hours, it would be reasonable to guess that the population mean would be 8 hours. It would be reasonable to guess it to be 9 hours. It would be reasonable to guess it to be anything between 7.77 hours and 10.73 hours. It would not be reasonable to guess it was 7 hours or 11 hours, for example. We can also compare two means, and the way we do that is we look to see if those confidence intervals overlap. If they overlap, then we think they might be the same. But if they don't overlap, then that's pretty good evidence that the two means differ from each other. So here we've got the number of hours spent watching TV per week broken down by male versus female. And we've got that this interval the interval for males is that they watch between 6.01 and 9.399 hours of TV per week. Whereas for females, that interval is 8.7 up to 13.577 hours per week. So it looks like females are watching a little bit more. But is it reasonable, based on looking at this, to guess that those are different? Well, the answer is no, because if you look at these on a number line, they overlap. So 6 to 9 hours has values in common between 8 to 13 hours. So it's reasonable to think that they might be the same. Let's check our assumption of normality. We don't have a large enough sample size. I believe we've got 20 children in each group, so we don't have a large enough sample size to assume normality. So we need to look at the histograms. If we look at these, this one is a little bit skewed to the right, but not too much. And this one's close enough. I would say both of them are close enough. If we had something where you had one super duper high bar over here and the rest of them were way down low, I would say that's too far of a departure. Or if you have something that's clearly bimodal. But here, these are close enough. All right, so that's it for this lesson. And, of course, please let me know any questions you have.